Good afternoon, everybody. Welcome to session 15. Yeah.
All right. Well,
this session is going to be chaired by Dr. Brent Robinson. So now let me introduce Dr. Brent Robinson. Dr. Robinson is currently Vice President, Pile Dynamics USA. Dr. Brent leads the research and development efforts, trains clients, and lectures internationally on dynamic testing, integrity testing, and installation of verification of deep foundations. He earned his PhD in civil engineering from North Carolina State University and an active member of the Transportation Research Board, Deep Foundations Institute, and International Association of Foundation Drillers. So I welcome Dr. Brent Robinson to chair this session.
Thank you very much, Dr. Rao.
Yeah,
and
due to some sudden emergency, the co-chair could not make it. So I will assist Dr. Robinson in discharging his duties as co-chair. Okay, thank you.
Thank you very much, Dr. Rao, for stepping in on short notice. And it is again my honor to introduce our SOAP lecturer, Dr. Vinod. Dr. Vinod, if you'd like to start sharing your presentation, that would be a good start. While we go ahead and do that. Dr. Vinod is an associate professor at the University of Wollongong in Australia. 1 second, let me bring that back up. He received his doctoral degree in geotechnical engineering right here in Bengaluru at the Indian Institute of Science, and then worked as a research fellow there and at the University of Wollongong before joining as a lecturer at UOW. His research is focused, and he'll discuss with us today, on numerical modeling of granular material and soil dynamics, as well as earthquake engineering and ground improvement techniques for rails and mines. He is an associate editor of the Journal of Materials in Civil Engineering for I.I.Sc, and a co-editor of the International Journal of Geotechnical Earthquake Engineering in the US. He's also actively involved on the Australian Research Council in the Cooperative Research Centre projects on ground improvement techniques, railway geotechnics, and mine tailing. He's published over 85 peer-reviewed research papers in reputed international journals and conferences. And today he will discuss with us his work on numerical simulations of coir geotechnical or geotextile reinforced soil under cyclic loading. And with that, Dr. Vinod, the floor is yours. Thank you very much.
Thank you very much. So thanks for that. And before starting my presentation today, I would like to acknowledge the organizing committee for giving this opportunity for presenting some of the preliminary work that we have carried out on the application of quire geotextiles for transport infrastructure development. Before going into the details of the presentation, let me give you some idea about where we are from. In Australia, we are here in New South Wales, and we are almost an hour drive basically south from Sydney. So that's where our main campus is located. So that's let me put some spotlight here. Yeah, so we are here south of Sydney, around an hour drive from Sydney Airport, and we do have campuses in Nowra, Batesman Bay and Bega for the south of New South Wales. Now, coming to this research that I am trying to highlight in this presentation today is basically a discussion that we have started with the Quiet Board Government of India a few years back, along with Professor Beena from Cochin University of Science and Technology, to see whether we can use this quire geotextile as an eco-friendly material for low volume road constructions in rural areas. So when we were looking at and investigating literature in this phase, we could able to find a lot of work on monotonic loading of these materials and carefully looking at the interaction mechanism of soil and coir geotextiles, but we couldn't find much details of this material performance under a cyclic loading condition, especially under a heavy, fast-moving truck or a high-speed rails, how this material is going to perform. Now, as you all know, we have quite a recent push everywhere to look at more environmental friendly materials for infrastructure development. I believe the coir geotextile is one of the best material that we can think of for using and developing infrastructure constructions. With that short background, let me quickly introduce our co-authors, Abdullah, who has done this work as part of his master's thesis, who has carried out this preliminary computational model. I just have to put that preliminary word here because this model has to be extended with some of the key features basically shown by coir geotextiles, which I'm going to highlight in later part of my presentation. And we do have collaborators from University of Leeds and I.I.T, who will be looking after the experimental part, looking at more towards interfacial friction during cyclic loading and micro chemical analysis in detail. And we have Professor Bina from Cochin University looking some of the details under the monotonic loading condition to help with this research. All right, with that, let's move on to the basic introduction as the problems associated with soft soils. And I'm sure there is no introduction required for this. And you all know that for a soft soils, it's always is associated with low bearing capacity, and you have high compressible material there. You can have very high consolidation settlements sometimes happening, and you have low permeabilities. And because of all these key properties, you can have failures happening onto the subgrade soils under different conditions. It can be from a truck loading, or it can be due to the drainage problem. So it creates a lot of infrastructure problems for practicing engineers. And you can see some of the key photos which shows how it majorly affects some of the major artery roads connecting to the main roads in these cases, which can affect the traffic a lot. So as a practicing engineer, if you face problems on soft soils, soft subgrade soils, what we generally go with is look at improving the soil strength by dewatering. And if you look at dewatering, we have a lot of technologies developed in hand. We have preloading, which is a pretty old technique, preload surcharge, or using you can see using the vertical drain. So you can see if you have a soft subgrade, you can use a preload and you can create additional drainage using vertical drains, and you can accelerate the consolidation process. So we already have established quite well information on how to improve the soft strength using these kind of techniques. Now, on the other hand, we do have materials. For example, if you look at the synthetic geogrids perspective, we do have geotextiles, geogrids, and geomembranes, which can basically provide a strength towards these materials, and which provides additional reinforcement effect for these subgrade for these subballast or sub-base materials. So you can see a couple of photos which I have shown here, where the geogrids have been used between the interface between the subgrade and the sub-base layer, which basically act as a reinforcement mechanism. And here you can see a combination of geogrid and geotextiles, which basically act as a reinforcement plus and a dewatering technique. So you can see a combination of both has been applied here to mitigate, for example, an effect of mud pumping in case of a railway track. So if you have a geotextiles here, it will try to dissipate that excess water pressure, which is developed due to the cyclic loading coming from a truck or a fast moving vehicle, can be dissipated through these geotextiles, and the geogrids can provide an additional confinement effect through the interfacial friction developed between the soil and the geogrid. So we are pretty much very much comfortable in applying or using this material for various infrastructure development. Now, the challenge or the key issues that we need to look at carefully here is during the maintenance period. Now, when it comes to the maintenance, especially in terms of railway, what basically happens is we have the machine which is running onto the railway track, and they basically pull the track, lift the track up, and compact the ballast into the track. So during the whole this process, what happens, what practicing engineers often observed is these geogrids got caught into this machine and becomes a very big issue for during the maintenance time. We do have observed some cases reported where this geogrid has to be completely removed for the realignments of the road, and in turn what happens, it becomes an additional waste as part of all these construction process. And as you all know, we are going towards more green kind of approach, and we are creating on the other side, we can see the waste from this material is creating additional plastic waste, which we would like to reduce as much as possible. And looking in that perspective, the application of natural materials like coir geotextiles and like example jute gives very promising prospects that it won't create any kind of natural waste materials and thus a low carbon footprint. Now, coming to the coir geotextiles, which I'm a bit interested today to look at and showcase some of the preliminary findings that we have from the numerical modeling. So those who are new to this, as you can see, coir geotextiles is basically a thin, flexible, permeable sheet made of coconut fibers, and that enhances the mechanical behavior of soil. And as I have mentioned earlier, we do have a lot of work carried out in this area for the last 2 decades to look at the improvement in the soil stability. For example, if you are looking at the slope stability, we have used coir geotextiles pretty comfortably in controlling the movement or the instabilities of the soil slopes. The advantage of having these kind of natural material is, according to me, this mechanism needs to be strengthened. It acts like two cases. One, in a short-term perspective, this material will behave exactly like a synthetic material, which provides a reinforcement effect. And in a long-term perspective, what happens is, due to the biodegradable nature of this material can leach lignin into the soil, which leads to a kind of a chemical stabilization later on onto the soil. So we have observed this kind of mechanism, but we need to understand a bit more into this mechanism and come out with a model which can be used comfortably by a practicing engineer to predict this behavior for short-term and the long-term perspective. Now, it improves the soil stability. Sorry. It improves the lateral resistance and increases the bearing capacity. And this has been reported widely by various researchers. So if you look at the geotextile materials, you can see we have PVC, polyester, and polypropylene and polyethylene. And on the natural side, we have coir, jute, bamboo, and palm. And you can see that coir and jute has been widely used for various construction. For example, the recent study that we have carried out at University of Wollongong is the application of jute drains compared to the wig drains, and how the performance of jute drains are compared to the wig drains. So it's quite interesting to look at how these natural materials perform in real practice. Again, we need to address a lot of challenges associated with the degradation of these materials for a long-term perspective. I'll quickly show you some quick photograph of the woven and non-woven geotextiles that we can have for different construction process. In this study, we look at more on the woven geotextiles for our numerical modeling. Coir fibers, as I highlighted, coir fibers are basically from the coconut husk, which is an external peel of the matured coconut. So that's how it has been prepared. And you can see that the chemical composition clearly shows that a high percentage of lignin content associated with these coir fibers. So that's has a positive effect on the degradation of the coir fibers plus the stabilization of this material in a long-term perspective. In short, you can see coir geotextiles we can have desirable engineering properties for these materials. It's eco-friendly, there is no doubt about it. And you can see the biodegradable nature of the coir geotextiles. And if I expand a bit on biodegradability, we can see that it has both advantages and limitations. So the major advantage is that you can see that it biodegrades, and in few years time the material disappears, and if the infrastructure we are looking at is only for a short-term perspective, we will get the maximum benefit out of this material in that time period, and then it completely degrades into that material. And if you are looking at an infrastructure, transport infrastructure condition, you can just mix the material up, and it becomes a kind of a fiber reinforced soil, which further enhances the properties of the subgrade material. So that's the advantage of it. And the limitation, as you know, it's whether we need to apply this material for a long-term condition or a short-term condition. That's where we need to draw a fine line. And that's where it is highly important to develop a biodegradable model to predict the applicability of this material for infrastructure development. So that is actually our ultimate goal in this research. So to come out with a computational model which helps the practicing engineers to design these structures, infrastructure for the years that they are going to design the infrastructure on. Right. With that broad aim in hand, we look at this material in terms of functions. You can see that the major function is exactly same as that of the geosynthetic material, like reinforcement. It acts as a reinforcement, it acts as separation, it has filtration, it can be used as drainage. Now you can see it's also performs exactly similar to the geosynthetic material. So only thing is that the biodegradability of the material needs to be considered in all these approaches. Some of the field application you can see here, it doesn't stop us in applying these materials to infrastructure. So you can see people have tried in using this material for low volume roads. That's road construction using coir geotextiles, slope stabilization using coir geotextiles. So we are trying to use these materials for different infrastructure construction, but we need to understand a bit more from the very fundamentals how this can be designed in the first place for long-term and short-term stability point of view. With that, let me quickly show you some work already being carried out experimentally on the bearing capacity or the load settlement behavior of this material. So you can see that which has been reported here. You can see that's a typical load settlement behavior of a unreinforced soil. You can see that's the applied pressure versus settlements. You can see that is basically for a unreinforced material, and you can see if you are reinforced with different coir geotextiles, you can see there is an increase in the applied pressure. So you can see the bearing pressure increases with the inclusion of your coir geotextile. So it clearly shows an increase in stiffness and an increase in the applied pressure or failure pressure with the application of coir geotextiles. Now, this is another experimental study carried out to look at the bearing pressure and the settlement for different reinforcements of coir geotextiles placed at different depths. So similarly, you can see here that's non-reinforced sand, and if you reinforced with different coir geotextiles, you can see there is an increase in the applied bearing pressure. So you can see there is a slight increase in the stiffness plus an increase in the ultimate bearing pressure too, with the inclusion of coir geotextiles. So basically what it shows here is with the inclusion of geotextiles, coir geotextiles, we can get an increase in stiffness and an increase in the bearing pressure with the inclusion of coir geotextiles. Now, this is some information about the geotextiles that they have used for this experimental work. Now, when it comes to the cyclic load, we could only find very few work on coir geotextiles. What I'm showing here is the work on geosynthetics. So you can see what I'm trying to show you here is how the settlement responds with and without reinforcement under the cyclic loading. So you can see here that is without reinforcement and that is with reinforcement. So how the settlement is controlled for different subgrade conditions using with and without reinforcement under cyclic loading. Now that's where the challenge we have. We could rarely find literature on the cyclic loading of coir geotextiles reinforced soil. Therefore, we are carrying out at our university a detailed large-scale testing on the cyclic loading of coir geotextile reinforced soil so that we can validate these models before applying to design any kind of transport infrastructure. Right, the degradation of the coir geotextiles. There is one study reported here how the reduction in the tensile strength is happening with time. So you can see that's a reduction in the tensile strength of untreated and the treated coir geotextiles. So that's some of the study which has been done to look at the degradation what we have observed on the onto these coir fibers. So with that, let's move on to the numerical work that we have carried out. So I divided that into part A and part B, where we look at in the first part very quickly into the monotonic loading, which we has carried out basically to calibrate the model. And we have three different conditions here to look at. The first one is the unreinforced, where we have a layer 1 we consider as a sub base and layer 2 as a subgrade. And you can see layer in B, in the second condition, we have a coir geotextiles going at the middle of the sub base layer. And you can see here in the third condition, we put it at the interface between layer 1 and layer 2. So these are the three configuration that we have looked at in our model. And our model we have which is a size of 500 by 800, which is basically similar to one of the literature which shows the load settlement behavior under monotonic loading. The material properties are pretty much same. We have looked at the well-graded gravel. We have looked at and we have placed reinforcement at the interface and at the middle of this subbase on the layer 1. And the reinforcement we have considered as a plate element, and we have used a linear elastic model. And for the soil, we have gone for a hardening soil model with hardening soil model here with small strain stiffness, so that we can capture the variation of the modulus with respect to the shear strain, which is critical for the dynamic analysis. The soil properties, I'm not going into the details of the soil properties here. So that's various soil properties we have adopted based on the work reported by Subaida in 2016 in one of the laboratory experimental work on coir geotextile reinforced soils. So after that, we compared and calibrated our model with the experimental data. And you can see that's unreinforced bearing pressure versus settlement response from this finite element model compared to the laboratory work reported by Subaida, and that's reinforcement at the middle and at the interface. So you can see here that's our model has captured the results very similar to the laboratory experiments. And you can see here at the interface, as expected, has shown a very high bearing pressure compared to the other reinforcement placed at the middle of the layer 1. We have plotted that in terms of N gamma here, nothing surprising. You can see the N gamma increases with the settlements and reaches a constant value at large values of settlement. So you can see that's a variation here for unreinforced, reinforced at the middle and at the interface. We looked at different layers of reinforcement, whether to see whether the number of layers can influence the bearing capacity, and we have observed that it's increasing the number of layers has an insignificant influence on the increase in the bearing pressure. So you can see anything greater than 2 has not contributed much on to the increase in the bearing capacity. So you can see that there is an optimum value that we need to look at when it comes to the designing inclusion of geotextiles into the infrastructure construction. We looked at the friction angle, how the friction angle is going to affect the bearing pressure. So you can see with increasing the friction angle, the N gamma increases as expected. Similar trend has been observed for the reinforcement at the middle and at the interface. So there is no surprising results here with increase in friction angle. We have observed an increase in the value of N gamma. And similarly, you can see an increase in the modulus that for the subgrade have also shown an increase in the value of N gamma for the reinforced material, unreinforced, reinforced at the middle, and the reinforced at the interface. So these are all results highlights that these simulation, our model is able to capture the response very, very similar to the laboratory investigation. Looking a bit more closely into what's really happening inside the sample. So you can see how the stress distribution happening here. So you can see that's a stress for an unreinforced soil. And you can see with the reinforcement at the middle, we could able to reduce a bit. But with the interface, you can see we could able to control the pressure very carefully in this by reinforcing at the interface of subgrade and the subbase layer, or layer 1 and layer 2. Looking at the axial force developed along the reinforcement, so you can see a more distributed axial force developed at the interface when the quad geotextiles is placed to the interface between layer 1 and 2 compared to the reinforcement at the middle of the layer 1. And you can see a very high axial force developed here compared to the axial force which has been reported, which has been shown at the middle of the reinforcement, middle of the layer 1. So you can see that's a more uniform type distribution, which has been very consistent and very similar to what reported by Kurian in 1997 on the variation of axial force along the reinforcement layer. All right, with that, I have only 5 minutes here. With that, let's quickly move on to the cyclic loading of quad geotextiles reinforced soil. We had gone through a bit of a challenge here without experimental data, how we are going to model the quad geotextile reinforced materials under a finite element or in Plaxis software. Luckily, we could able to find one literature by Sridhar and Kumar looking at the cyclic loading of a quad geotextile reinforced soil in a fully immersed sand condition. So we picked up that to calibrate our numerical model. So you can see that we have simulated a different condition very similar to what the laboratory experiment work has been reported by Sridhar and Kumar, and we have tried to capture with our model to see whether we can capture the variation of settlements with number of cycles very similar to what they have predicted in their paper in 2018. The challenge here is to to develop a cyclic input for in Plaxis software to capture this behavior. So that was one of our key challenge in modeling or extending this model to capture the behavior under cyclic loading. So you can see that with the new input that we have created in Plaxis, subroutine developed in Plaxis, we could able to capture the settlements versus number of cycles, very similar to what has been reported by Sridhar and Kumar under cyclic loading condition for a cyclic stress of 100 kPa and with a frequency of 0.5 hertz. It's a very, very small frequency for a traffic condition. We then extended that model very similar to the layer 1 with 2-layer system, which we have calibrated in the monotonic condition to look at the effect of the amplitude of a cyclic stress and frequency on the performance of the quiet geotextile reinforced soil. So we have used the same kind of amplitude here, and you can see the response of the model under different amplitude of cyclic stress. So you can see with the increase in the cyclic stress, we can see the settlement increases with the number of cycles. So we can see that we run this program up to 10,000 cycle, which possibly take around 3 days, close to 3 days to run this simulation under these kind of grid conditions. So you can see that's for the reinforced at the interface and at the middle. So you can see that if you look at the table carefully, you can see the reinforcement at the middle has shown a very high performance compared to the reinforcement at the interface. So slightly different behavior that we have observed compared to the monotonic loading in this case. Now, we have looked at the effect of frequency like 0.5 hertz, 1 hertz, and 1.5 hertz. I still tell you that's a very small frequency when we are looking for a transport condition, but still it captures the behavior of frequency under different conditions like unreinforced, reinforced at the interface, and reinforced at the middle of the layer 1. And similarly, you can see here the performance is slightly better when the quiet geotextiles reinforced is at the middle compared to the interface under the cyclic loading condition. Now we looked at that. What's really happening here? We have kept everything same, exactly similar to the monotonic loading condition, but we have observed a slightly different behavior compared to the monotonic condition. And then we looked at very closely into the axial stress developed on the quiet geotextiles, and we have observed that a very high magnitude of axial stress has been, or axial force has been developed when the quiet geotextiles is very at the mid of the layer 1 compared to the interface. That probably due to the kind of load application that we have used under both static monotonic and the cyclic loading, where in the monotonic loading condition, we have used a strain controlled approach, and here is a load controlled approach. So we can see there is a significant difference when the application of the reinforcement due to the application of the load or the type of loading that we are trying to do. Further, we need further experimental evidence to highlight the findings that we have observed here. That is currently in progress. So with that, let me quickly conclude that this numerical model, the preliminary numerical model, captures the soil bearing pressure versus settlement behavior, very similar to the laboratory experiments reported by Subaida and Sridhar and Kumar for both monotonic and the cyclic loading. Quiet geotextiles were installed at the interface between layer 1 and 2 and in the middle of the layer, and placing the quiet geotextiles at the interface have led to the optimum performance under monotonic loading. There is no surprise. A lot of work has been carried out, and basically this is strengthens their findings in the application of the quiet geotextiles. Now, the number of layers, I have already highlighted that number of layers has shown an insignificant influence for n greater than 2. The application of quiet geotextiles between layer 1 and 2 reduces the settlement around 38%. So I indirectly calculated the reduction in the settlement for synthetic, which is very, very close for a short-term perspective. So this material can behave very close to the synthetic materials in that the time frame that we are looking for. So the performance is quite good. We didn't have a direct comparison, but an indirect comparison shows that it can perform very similar to the synthetic materials. So the inclusion of coir geotextiles in the middle of the layer yielded the best performance under cyclic loading condition. And please note that it's considering the cyclic stress that we have considered in this investigation, which requires further validation using further large-scale experimental test data. The settlement was found to be increasing in cyclic loads and the frequency. The interface friction between the soil and the coir geotextiles generates an interface shear strength and an axial force in the geotextiles that basically contributes towards the increased bearing capacity and reduction in the settlements. Limitation, I need to be very careful about the limitation of application of these coir geotextiles for different infrastructure construction. First thing is that the coir fiber degradation and its effects on the response of reinforced soil. So it is very critical that we develop a model which captures the degradation of the coir fiber, and that needs to be integrated into any model to capture the short-term and the long-term perspective. So if we can able to predict the time frame up to which this material is going to perform, and that is exactly what a practicing engineer will be looking for before applying this or a wide application of this for any infrastructure development. Effect of different sub-base and subgrade material, including stress rotation during traffic loading, needs to be investigated. High frequency, we have only looked at around 1.5 hertz, which is very small for a traffic condition, and we need to look at a very high frequency and very high cyclic stress amplitude before applying this to any kind of payment infrastructure. And finally, we need a large-scale validation of the model with detailed large-scale and field investigation, which needs to be done before applying this to any field application. With that, I would like to acknowledge Coir Board, Government of India, Faculty of Engineering and Information Sciences for funding this research project, Australia India EMCR Fellowship from the Australian Academy of Science. I would like to thank Mr. Radhakrishnan and Dr. Ananda, Director of the Coir Board, former Director of the Coir Board, for providing financial support and coir geotextiles for this research, Professor Bina from Cochin University, and the computational and laboratory facilities at University of Hong Kong. Thank you very much. I think I exceeded few minutes. I'm happy to take questions from the audience. Thank you very much.
Thank you very much, Dr. Vinod. It was an interesting presentation of your preliminary efforts, and we look forward to seeing some of that go final in the coming years. A question from the Q&A part of the chat. Harsha is asking, in general, the tensile strength is the predominant property of geotextiles, and also we are concerned with the horizontal and vertical elastic modulus of the geotextile and how they are different in their direction of loading. And so how do you manage that behavior with a plate element and a linear elastic model?
Thanks, Harsha, for that question. It's a very interesting question. In this model, unfortunately, we did not look very closely into the modulus at different directions, like horizontal and elastic modulus. We didn't look at in that perspective. Since we have used only a plate element with linear elastic, we are majorly looking at the axial stresses that has been developed onto that reinforcement element. So I truly value your question. I think something which probably we have to look at in future in calibrating the plate element with more experimental data, and see whether we can capture the best element, for example, for capturing the deformation behavior or the axial stresses developing onto these coir geotextiles. I'm not sure whether I answered your question, but I don't have a direct answer for that question because we didn't conduct work in that area. Thank you.
Thank you, Dr. Vinod. One question from me. Are you how much of the difference do you think that you're seeing in the laboratory studies is an effect of the reinforcement aspects of the coir geotextile versus any separation or filtration effects? Are these the grid style coir, or are these that you're modeling, or are these more of a textile that would provide more filtration and separation to prevent migration of the fines from the clays up into the gravels?
Currently, we are looking at kind of even it's a kind of geogrid type where we have aperture size, different aperture size. We are looking only one particular type of aperture at this point of time to see whether this can perform well for that type of subgrade materials that we are looking for. As I have told you, very few work has been conducted in this area, even to look at, for example, the effect of aperture size on looking at the reinforcement effect, or even the filter or the separation effect of this material. So in this study, what we have done, we, as I have clearly highlighted as a plate element in a 2D phase, we cannot capture all those aperture effect into the model. So it's we have not gone to that area. This is just a beginning to look into a more realistic goal in the future to see whether we can come out with a robust model to capture some of these key factors.
Well, very good. As you said, I think that we need to move on to our paper presentations. Again, Dr. Vinod, thank you very much for your presentation and your time. And we will look forward to future results on this subject.
Thank you very much.
Can I have one question, please?
Yes, go ahead,
Sure.
Dr. Rao.
Yeah. So thank you, Professor Vinod. Very interesting presentation. But there is a serious limitation comparing to synthetic material, because coir has certain limited lifetime. Even all the laboratory testing results are applicable only at the time of installation, but with the time they degrade. So there is serious limitation about that. And whenever this degradation takes place, the changes we are expecting should be improved before the degradation takes place. So as of now, they are using right now only for the slopes, where if you plant some grass or something, that grass will grow and induce the properties which we require by the time this degrades. But I am not sure how it is going to help in terms of improving the bearing capacity and all, because it will start degrading in certain amount of time. And regarding one more, where you are shown by increasing the number of layers, there is no improvement. You are shown one plot. There, my concern is that you have increased the number of layers beyond the pressure bulb. So obviously they will not have any effect. But conventionally, if you see the number of layers effect and all, if they are within the influence zone, then they may have some improvement. That's only my one comment. Thank you.
Yeah. Can I answer the first
Please,
point?
please.
Yeah, thank you for that question. It's a very interesting question. I completely agree with you. That basically stops the application of coir geotextiles for different infrastructure construction. So basically, the biodegradability has advantages and limitation. But what we are looking at here is there are a lot of practical application on the other side where we can use this material. For example, mine haul roads. It's only a temporary infrastructure that we require during the construction of the mine. So there are a lot of other, for example, low volume roads which connects to the main artery roads. So there are a lot of areas that where we can focus on in application of this material, and we can see that once the mine is closed, they don't want the plastic to be inside. So they want something which is natural, which degrades quickly. So I can see there are potentially a lot of application in the future where this material can be used for various infrastructure construction. And as you said it rightly, we have used this for slope stability, and I'm very much aware of that work has been carried out on the slope stabilization. There are two things which we didn't understand very carefully. One is the effect of these coir geotextiles in stabilizing the lateral movement using the reinforcement condition, and second is the leaching effect of the lignin into the soil. And this has a chemical binding which provides the soil. So we didn't investigate this mechanism very, very carefully, how this effect of leaching the lignin into the soil affects the chemical stabilization effect. So there are several mechanisms which is underlying to this material, and I think we need to do a careful investigation to make sure that we get the correct knowledge around this material so that we can apply to the practicing engineers later on. And that this is a humble effort towards that major goal. Thank you.
Well, thank you very much, Dr. Vinod. I wish we could talk more about the biodegradability. Maybe we can take that offline.
Thank you.
But we do need to move on. If you want to stay till the end, if we have some time, we can maybe circle back and ask some more questions.
Sure.
Our next presenter is Dr. Arthi from the I.I.T. Madras, discussing the effect of influencing the effect of influencing parameters on the failure mechanisms of sand compaction column treated cohesionless deposits. Dr. Arthi, if you would like to share your screen, we can then go ahead and your 8 minutes can begin for your discussion.
Are you guys able to see my screen?
Yes, we are, and we can hear you very nicely. Thank you.
Yeah, thank you so much. 1 minute. Is it fine, sir? All good
Still
to go?
good. Thank you very much. Go ahead.
So,
And can you introduce yourself briefly?
sorry?
And can you give yourself a brief introduction too?
Yes, myself, Aarti Natarajan, and I've recently completed my doctorate in Geotechnical Engineering from Indian Institute of Technology, Madras. I'm presently working as a lecturer in near my hometown in Tamil Nadu. And I'm very happy to be here to present my work. This is one among the part of my PhD work, and good to meet you all for this nice occasion. So let us start with, I'll try to stick to the timings, and since I have a class to go. And yeah, so this is basically about one among the ground improvement techniques called sand compaction piles. And this is a very specific topic that will be keenly focusing on the effect of influencing parameters on the failure mechanism of sand compaction column treated cohesionless deposits. So this is a picture over here where we could clearly see in a field application. This is a casing that has been used, I mean, most of the cases. This is the one among the casing equipments, type of casing equipments that are often used in the field applications to install these sand compaction piles. And I thought it is very, very appropriate to put this picture over here on my front slide so that everyone right away understands what I mean by sand compaction pile. And coming to the outline of my presentation, and this is how it will go. And introduction and motivation, I mean, motivation behind the study or the reason to carry out this study, and the sand compaction columns, what are they? And the research gap behind this, I mean, what exactly is the gap and where my work is fitting right into the literature graph, and coming to the finite element modeling and failure mechanism of sand compaction columns and the parametric studies and the conclusions. And this has been taken in a actual site near Ghaziabad in Delhi, near Delhi. And this is where the sand compaction piles has been carried out already in the field. And you could see it is of a square pattern, and it is already installed in this particular layout, and it is yet to be installed over there, and the workers are doing on it. And this has been taken from this article, one good friend of mine. And yeah, so straight away into the topic. So I just want to introduce the topic to you all guys. And basically in India, as far as India is considered, we have majorly 3 problematic deposits. These are loose sands, marine clay, and expansive soils. And among these, my topic or my area of work is on loose to medium sand deposits to improve their bearing capacity, etc. And when you just keenly look upon any type of granular column inclusion, I mean, vastly there are 2, stone column and sand column. And as far as stone column is considered, you have n number of articles so far, and the entire Western Hemisphere is actually done so much about stone column. And sand column is a thing that has been, we could say, the contemporary of a stone column, and it is much more very famous in the Southeast Asian countries, including Singapore or Japan. It is a method which has been invented in 1956 in Japan. I mean, the art of carrying out a sand compaction pile or column, whatever you can name it. And as far as this topic is concerned, while moving on to the inner versions of finding how sand compaction pile installed cautionless deposit, that is improved caution deposit fails and their failure mechanisms, and how far, what are the parameters that would affect such improved deposits in real-time application. So that is what is my cup of tea as far as this article is concerned. And yeah, as you could see, as stone column, a lot of people have already researched it out, whereas in comparison to sand compaction column, and yeah, one such work have been carried out from Maccabee and Killeen for stone column, and that has been a detailed study. And this particular study is, I would say, a contemporary to this particular work on stone column, as far as the SEC is considered, sand compaction pile. So this is the motivation. We didn't find any, I mean, we were not able to find any lot of literature or very critical findings as far as improved deposits of SEC improved deposits, and especially cautionless deposits were considered. And what will be their failure mechanism? How will the wedges move? How will the shear strength mobilize? In what way? Like that. So this is the problem behind. And to give a very short introduction about sand compaction columns, it is one among the ground improvement techniques, and especially for sands. We have blasting, vibratory probe, vibro compaction piles, and heavy tamping. And this is one among that. And it is a displacement technique rather than a replacement technique for stone columns and clays. And why sand compaction column? And because one can go for it because it's simple, cost effective, and fast. And usually this is driven by a hammer or static compaction or vibratory. And hammer driven is the method of invention, I mean, method of driven technique that has been made while it was invented. The entire overall scenario was invented. And this is a short pictorial representation. Hope it is self-explanatory and anyone can literally interpret from what is happening. So this is the vibrator poker or vibrator, whatever. And we can just fix it on the side, and upon giving some energy, it is pushed down and sand is filled. Top feed, bottom feeds are there, and this case is the top feed, and just retrieving and compacting the entire sand compaction pile or column is formed. And this is the extraction graph over time. How do the penetration varies over time? And this is that, and this is the casing tip movement. And yeah, coming to the research gap. So as for the stone, I told you already that is stone columns are contemporary to sand compaction columns, and stone columns have any number of articles to go for. If you want to have a look at static loading in stone columns, you can go for this, and cyclic loading, you have a number of articles. Lateral loading, you have stress sharing mechanism, you have failure mechanism of SC in clays, you have, but in these kind of in-depth studies or very, very hard to find as far as SEC in cautionless deposits are considered. I was able to find only this particular study, that too in clay only, and in sand, there is literally hardly any. So this particular attempt is addressed to fit that gap of having a failure mechanism study of SEC in cautionless deposits. So this is what is my research gap, and hope that is clear. And so far, only one article has been, has been reported on SECs in clay, that is by Tarashi et al. At 1991, where there is a pictorial representation. Those times they were only, not such sophisticated softwares were available, so only a clear picture of a photograph was being given, reported in that particular article. And my present attempt will be like how the failure wedges are going to make a move when compression loading is applied on the top of the foundation. So yeah, aim is clearly represented. I hope so, and to study the failure mechanism of SCP improves deposits, sand deposits for variations in parameters. And These parameters are four in order: initial relative density, diameter of the compaction column or pile, whatever, and column length and spacing between the columns. And this is this particular article deals with only the numerical study and only for the prescribed range of parameters, and they'll be given below. So this is the prescribed range of parameters for each of the parameter taken. And we have created a base model using Fluxus 3D, and whose initial RD is 30%, and length of the pile is 20 meter, and diameter of the SCP is, our SCC is 0.6 meter, and spacing between these piles is 2D. So this is I hope this will be a self-explanatory figure where you can clearly see the soil cluster, soil domain, soil volume, and the pile cluster in the center. Only the center three piles will be loaded for its behavior, and it will be surrounded by a row of piles such that it will replicate the field situation. And the entire domain is for 25 by 25 by 25 meters, such that it will clearly represent a field scenario. So yeah. Coming to the in-depth view of the having a feel about how the failure mechanism is happening, or how far the wedges are going, or what shape it takes. So this is how it has happened. It is happening when we have a section at the center of the domain, like what we had in the previous picture. Like that, we have taken a section at the center, and this is how the wedges protrude through the improved deposit. You could clearly see that the wedges, these are just the superimposed lines to clearly explain how the wedges move. And you could clearly see a Tersagi's failure wedge, and which minor changes over here, and instead of a logarithmic spiral, and you could see the spiral wedges deepening here. And this is for the base model range of parameters, value of parameters. And now this particular base model is subjected to the parametric study for keeping all others constant. Each one parameter will be changed at each time, and the analysis is performed throughout this entire article. First case, effect of initial RD with all other parameters being constant. We are just changing the initial RD alone. And this is for the representation. This is how the results are we are obtained. We have obtained, and the failure wedge formed for the cases of lower initial RDs with prescribed settlement here. In these cases, the wedge is formed similar to that of the Tersagi's theory. However, when you increase the RD and the spiral portion of the wedge deepens along the periphery of the SCP group, you could clearly see the wedges coming down here, in this case, immediately below the foundation. And this is the foundation, and this is where the foundation plate will be. And you could see upon increasing the RD, the failure wedge is tending to go down immediately below the foundation plate. And coming to the effective pile diameter, you are increasing, we have increased the 0.5 to 0.5, 0.6, 0.7, and 0.8. Here also the same kind of behavior is happening, where you could see that the immediate layers below the wedge for the smallest diameters are resembling a Tersagi's failure wedge. And whereas when you increase the diameter, you could see the immediate vicinity below the foundation is like the wedges are tending to come down, or it is not anymore a Tersagi's failure wedge. And yeah, this is the inference from this. And coming to the pile length, we have critical pile length and the exact pile lengths. And for critical pile lengths, the deformation extends up to the bottom of the pile like this, within 5 meters. Whereas for the other ranges, 5, 10, 15, and 20 meters, we have a nominal wedge. And you could see for 5, 10, and 15, and 20, all the cases, the Tersagi's shear failure, you could observe here below the full foundation, footing. So we can come to a conclusion in this case. Irrespective of the pile length adopted, the SCP improved portionless deposit undergoes general shear failure. And coming to the next spacing,
Dr. Arthi, I'm afraid we have to wrap it up here shortly, so please, one more minute.
Okay, so coming to the conclusion, yeah, the failure mechanism of the footing resting on sand compression pile is a general shear failure with a failure which is similar to that of tertiary shear failure. And it is mainly governed by pile spacing and pile diameter. However, others are also found to have some effect on it. And this is obtained for different cases, and this is expected to affect the load settlement behavior of the improved deposit also. So yeah, and thank you for the patient listening. Yes, sir. I'm done, I think.
Thank you very much. I know 8 minutes is a very short period of time to present a lot of very obvious effort and work. I don't see any questions in the Q&A, and I guess the one of the things that you showed in your in the installation of SCCs is that oftentimes as it pushes into these soft clay materials, it will tend to make a larger diameter. And what do you think the effect of that non-uniformity would be if you had a non-uniform section as opposed to a uniform one?
Yeah, it is like for clays. Actually, I hope it will have a tremendous effect, because my entire study was purely on questionless deposits. However, so frankly speaking, I do expect a tremendous effect in the case of clays. Yeah, having not done any technical experiments on clays, I think this will be the expected outcome as far as now is considered.
Sure. All right. Well, thank you very much.
Yeah. Thank you.
Next, and thank you for your presentation.
Yeah.
We need to move on to the next talk from, let's see, Prudvi Mamidala from the Karunya Institute of Technology and Sciences in India. He will be discussing stabilization of black cotton soil using salts and their comparative analysis. If you could share your screen, that would be a good spot, and we can go ahead and start the discussion.
Is Prudvi there? It appears he's not there. Maybe we can proceed to the next one.
Okay, well, that works. Moving on then. Mohit Mistry is going to give us a presentation from Surat, India, discussing the use of waste tire fibers as a reinforcing material for road subgrades and comparing laboratory analysis with that. So Mohit, if you wouldn't mind starting up and sharing. Very nice to see you. And I can hear you very nicely. Go ahead and share your presentation and we can get started.
Okay, is it visible now?
It is visible now and we can hear you. Thank you.
Okay, thank you. So myself, Mohit Misri, I'm a PhD scholar from NIT Surat. I have recently submitted my thesis. So I'm about to at the end of my PhD journey. So today I'm going to present my a small part of my PhD work, that is the use of waste tire fibers as a reinforcing subgrade material. So I have done the comparative analysis between uncoated fibers and cement coated fibers. So before starting my presentation, I would like to acknowledge my co-authors, MTech students, and my mentor Sanjay Kumar Shukla, and my two supervisors, Dr. Shruti Shukla and Dr. Chandesh Solanki. So it is my layout of my presentation, starting with some of the background about fiber reinforced soil engineering, then what are the materials I have selected, and then result and discussion. So in top left figure, you can see that as you all know that the soil is very poor in tension and it is very good in compression. So to increase this tensile resisting capacity, we are embedding the tension resisting elements into the soil. So in top left figure, we can see that we have embedded some continuous reinforcement. It is like it is shown as woven geotextiles. So here we can see that we can apply reinforcement in systematic layer in particularly fixed predefined layers, or we can say that we can place it in predefined one-dimensional direction. So same way on right hand side figure, we can see that it is slope retaining wall is reinforced with the fiber reinforcement. That is a discrete reinforcement, and hence in that particular reinforcement in one dimensional or particularly in systematic layer is not possible. So it is not a new technique, it is an old technique. 5,000 years ago, Mesopotamians and Romans have separately used this technique to improve their road paths. So this Great Wall of China and Ziggurat Babylon is two of the famous ancient structure which was constructed using this technique. So these are three different types of fibers: natural, synthetic, and waste. I will not go into the detail of this. So with ever increase in modern civilization, we can see that the growth of industries has been increased, and because of that, number of vehicles are also being increased. And as per this ATMA 2017, per day in India, 6.50 lakhs tires are being produced, and their production will increase up to 60% by 2022. So in this figure, we can see, in this plot, we can see that how fast it has been increased. And from that 6.50 lakh tires, 2.75 lakh tires are being converted into the waste per day. So for a lot of the governments of world, it is a chronic issue that should be solved. So because it occupies 80% of the voids in this debt, and it also occupies more land for its disposable. So it is also more prone to fire hazards. So these are the famous fire hazard which is happened due to the tire fires. So I will not go into the details. So, and these are the recycling system, or we can say the pulverization system for the different end products of the tire. Because of the time constraint, I will not also go into these details. So these are the various products which are being used in civil engineering constructions for different purpose. So for this particular study, we have our main objective was to check the benefit of these tire products in the form of fibers for the reinforcement of the cohesive soil, which is used as a pavement subgrade material. So these are the four materials. As a unreinforcement material, we have used a clayey soil, which is having this liquid limit, plastic limit, and as per this IS classification, it is a high plasticity clay. And then OPC 53 grade cement we have used to coat these fibers, and these are the uncoated fibers. So both type of the fibers having aspect ratio around 4.5. So better image can be seen over here, that it is having very good rough surface, and it is having sufficient thickness, which will help in our reinforcement mechanism. So this is the basic gradation of the soil. And generally these waste tire fibers are having specific gravity varying from 1.13 to 1.36. But whatever the fibers we have used that are without the metal content, that's why whatever the fibers we have used, it is having specific gravity 1.15. So totally 9 compaction tests were conducted using 0.25, 0.5, 0.75 and 1% fiber content, and 0 that is unreinforced soil. So here in the fibers were mixed with the soil with the dry mass of soil, because fibers are having non-uniform shape, hence the volume fraction was not possible. That's why we have added fibers into the soil with the mass fraction. So total 8 compaction tests with uncoated fibers, then 8 compaction tests with the cement coated fibers, and 1 test for the unreinforced soil. That's why total 9 modified compaction tests. Similarly, 13 CBR tests were conducted to simulate the field condition as a normal rainfall and heavy rainfall. We have conducted under unsoaked and soaked condition. So total 13 number of CBR tests were conducted. So first question arises that how we have coated the cement fibers. That initially from the literature we have several options that we could mix the fibers into the soil in dry form, or we could prepare the mixture of the soil in wet condition, and then we could have add our fibers. So here in this our case we have used cement, OPC 53 grade cement, which with the 30% water content. The reason behind selecting the 30% water content was that OPC 53 grade cement was having liquid limit varying from 28 to 33. So on an average 30% water content was used to prepare the cement slurry. Even in the cement slurry, we had several options that 1:1, 1:1.5, and 1:2 fiber cement ratio we have used. In that also, maximum specific gravity was achieved with the 1:2 fiber cement ratio. That's why for the further study we have used this proportion for the cement coating. We have tried 1:2.5 also, but in that the lumps were created and the improper coating was done. That's why we have stick to this 1:2 proportion for the fiber cement ratio. Now for the curing period of that cement slurry, we have used only 24 hours, because after dipping the fibers into the cement slurry, we wanted to maintain the flexibility of that fiber. If we could have used more than 24 hours, then fiber may get brittle, and it may affect the, it will not serve its purpose of that good tensile strength. So for that, we have used only 24-hour curing period. So after preparing the coating fibers, we have mixed all the fibers in dry condition, and then required water content was added to the fiber soil matrix. So coming to the resultant discussion, the fluctuation in compaction tests were seen in OMC and MDD always. The modified compaction tests were conducted as per the IS part 8, and the fluctuation in OMC was seen, that is because of the rough surface of the fibers, and it is having non-uniform shape. So in some of the cases, the water will absorb, the superficial gap will absorb the water, and it will enhance its OMC. Similarly, in some cases, the density of the fiber clay matrix was reduced. That the one reason for that is that fibers are having a lesser specific gravity as compared to the soil. That's why overall fiber clay matrix will give the lesser maximum dry density in each case as compared to the virgin soil. But in the case of we have tried the standard Proctor test also. In that, specific gravity was reduced, but maximum dry unit weight was reduced. But with the application of higher energy, that means with the modified compaction test, the density is also increasing. So coming to the CBR results, for the better results for these fiber, we can see that from the load penetration curve, that here this star line, this shows the unreinforced soil. Here we can see that after certain load increment, the curve becomes flatter. Wherein in the case of reinforced soil, the load penetration resistance is being increased gradually. So we can say that the high tensile strength of the fiber is playing its more role, as well as we can see that the initial portion, the discrete fiber will delay the development of the failure plane. So hence, it is even the fibers are having high energy absorption capacity. That's why it can resist more load. So similar pattern we can see that in next successive graphs also. So this first graph is for the uncoated fiber with unsoaked condition. So second one, you can see that it is a cement coated fiber with unsoaked condition. Here also you can see that as compared to this unsoaked fiber, we can achieve, we are achieving almost that maximum penetration is achieving up to 10 kilonewton. Here also it is around 11. So we can say that in unsoaked condition there is not much variation with the cement coating. But so the better results of this can be seen from the CBR value. So here also we have shown the CBR value of 2.5 mm and 5 mm penetration. So in practice, usually we are using the 2.5 mm value for this pavement design. So here you can see that with the 0.75% fibers, we are achieving higher CBR values for all the cases, 2.5 mm and as well as 5 mm penetration. So now this is the next case for the soaked condition. So first is this uncoated fiber. You can see that the virgin soil shows the very flat curve at with the only 0.25 kg load, where with the addition of the fibers it enhances greatly. So that energy absorption capacity of the fiber plays an important role. Similarly, in cement coated fiber in soaked condition, you can see that it is enhancing even more. So here you can see that for the 2.5 mm penetration and 5 mm penetration, for the 0.5 and 0.75%, it shows the higher results of the CBR value. You can see here that initially in soaked condition it was only 2, but with the addition of the cement coated fibers, it shows the around 13 to 14 fibers. That means it is enhancing almost 6.5 times with the addition of this cement coated fiber. So if I go for the conclusion in short, that in unsoaked condition, CBR of subgrade value is for the uncoated fibers achieves for the 0.75% fibers. And you can see that in uncoated fibers in unsoaked condition, it is almost becoming constant after this 6 mm penetration, and even that higher peak value is achieved only with the 0.50% fibers. And here you can see with the better results with the CBR value that initially it was around 10, but with the addition of this, it is achieving almost 16. So almost 2 times it is enhancing for 2.5 mm and 5 mm penetration. Similarly, in unsoaked condition, overall in uncoated and coated fibers, it is enhancing 3 times to 6.5 times. But major benefited results can be seen for the soaked condition, because in on-field, usually in soaked condition, soils are giving lesser CBR values. But with the addition of the cement fibers, as compared to uncoated fibers, the cement, as compared to unsoaked condition, in soaked condition, CBR values are more. You can see that it is enhancing up from 2.8 times to 7 times, wherein unsoaked condition, it is only up to 6.5 times. So we can see that the addition of the fibers can enhance the, can give the better results for this use it as a reinforcement material. Even it is a more economical, we can say that it is an economical option. And yeah.
All right. Well,
thank you.
Thank
Can
you
I have
very
a quick
much.
question?
Yeah, actually,
Yes.
they are eating up the question time also. Presenters should be careful, no, not to take so much time. They are spending too much of time on introduction.
Yes, it's a difficult side here, but maybe we can meet at the end and hold that question for the next 2 presenters. And if we have a little bit more time, we can go ahead and do that.
Yes.
So let us go ahead and again, there is a question, please hold it. Let's go on to our next presenter, if we can get that up by Padmanabhan at the Indira Gandhi Center for Atomic Research in Kalpakkam, India. The efficiency of consolidation grouting in improving dynamic characteristics of nuclear facility foundation strata. And so please saw that they were on. Are they still here? See if they have.
Yeah, he's there. Padmanabhan is there. He is there.
Okay, very good. If that could be, bring up your mic, turn it live, and go ahead and share your presentation. Majid Hussain of NIT Srinagar. Majid, if you want to start putting on your mic and opening your presentation. This discussion will be on the pore pressure response of natural soils under various testing conditions. And again, please do watch your time. Hopefully we can get the other 2 authors back up with their. Hello, Majid. We can see you and we can see your presentation.
Yes, good afternoon, everyone. So today I will be speaking about the pore pressure response under different conditions. So the brief outline of my presentation will be like, we'll first give a very brief introduction about the pore pressure response, and then we'll discuss briefly the materials and methods. Yeah, after that we will go with the results.
Yeah.
Then briefly discuss the conclusions and then references, right?
Yeah.
So if you look at the stress response for the monotonic drain and underloading from the basic constitutive material of the constitutive behavior of these materials.
Can you please speak the mic closer to your mouth?
So we can see that under drain conditions, so there is change in the volume and we allow that. So if that is restrained and we are going into the undrained conditions, the pore water pressure develops. So be it static loading or cyclic loading, then it will be there. Then how it is allowed to drain, that will actually determine the soil behavior. So in case of monotonic undrained loading, we can see pore water pressures leading to static liquefaction. So similarly, under drain and undrained cyclic behavior, if we are allowing the volumetric change, that will lead to the settlement. In undrained case, that will lead to the development of the pore water pressure, which ultimately leads to earthquake liquefaction under load. Now there is a link actually between the static and the cyclic the response under undrained conditions. So in any case, we can see here on the left that the cyclic stress path hardly goes beyond the instability line, the red one that is shown here, that is the instability line under the undrained monotonic conditions. Now under cyclic loading, you can see that it does not go beyond that. However, it always lies beneath this drained loading bar, that is actually the morphophilic annulum. Similarly, under cyclic loading, so if we see the stress bar, so that has a particular relationship with the undrained monotonic loading. Now, in materials and methods, so what we had actually, so in 2001, there was an earthquake in the Indian state of Gujarat. So it was a 7.6 magnitude earthquake. So, and there was devastation from structural as geotechnical perspective. So we collected actually 32 soil samples from 10 locations, which include around 5 dams and 5 residential areas. So there was very large variability, both in you can say fine content, plus characteristics and density. So these are the material parameters, we can say index properties of the soils, and around 19 of the soils were actually cohesionless soils, silty sand and sandy soils, and few of them were actually clay soils. So these are the basic properties, index properties of the soils up to depths of 2.5 meters, and we can see that clay content was actually varying also, and fine content reached up to 83%. Now, regarding the testing, we did both a monotonic compression fracture tests under undrained conditions and cyclic tests. So all the tests were actually deformation controlled, and cyclic tests we had cyclic fracture tests and cyclic simple shear tests. Now on the presentation, we can see that under cyclic simple shear loading, we have load in the horizontal direction under an applied effective vertical pressure. And in all the three tests, we have 100 kP of effective vertical pressure. Now, looking at the pore water pressure response, so we are actually comparing how this pore water pressure changes or develops for the three conditions and its variation with the fines content. Now, as we see here, so we have chosen here the first cycle under cyclic conditions, that is the cyclic triaxial and the cyclic simple shear, and at peak for the monotonic compression loading. Now we can see here that with fine content, the pore water pressure that develops is decreasing, and that is actually obvious. However, if we look at the fifth cycle, we can see that most of the soils has reached the pore water pressure ratio of 1. That is the pore pressure equivalent to the effective confinement, which leads to actually an effective the stress nearly equivalent to 0, and ultimately leading to a negligible shear strength. Now, if we look at this variation of the pore water pressure with respect to the plasticity index, now we can see that for the soils that are actually cohesionless, that is plasticity index nearly equivalent to 0 or near about to 0, we can see that the pore water pressure that are very large pore water pressures ranging from 0.5 to 1. So we can see for cyclic triaxial tests that are the gold dots, and for cyclic simple shear tests. So cyclic simple shear tests, they actually develop very large pore water pressures as compared to cyclic triaxial tests. And we know that the cyclic simple shear, this apparatus actually represents the earthquake condition and how do the shear waves travel. It simulates them better. And similarly, at fifth cycle, we can see under both the conditions, be it cyclic triaxial or cyclic simple shear, the soils have liquefied. So the soils have actually very low inherent this liquefaction resistance. Now, if we look at the grain size index of the soil, so grain size index, that's a parameter that is actually related to the distribution of the soils, the particle size distribution of the soils. So it is actually a ratio covering the representing actually how much area is under the grain size curve and how much of the area is lying between the particle size of 0.001 mm to 75 mm. So basically, it removes very heavy particles which are actually very less susceptible to this liquefaction because of the heavy gravity force, as well as it discounts for the very small particles which are cohesive. And we know that the cohesive soils are very heavy boulders. They are not susceptible to liquefaction. It is the soils that have very low weight and very low cohesion that are actually susceptible to liquefaction. Now we can see for the soils in the Gujarat region of Kutch, so most of the soils are lying within this range, 0.4 mm to 0.8 mm. That is silty sands, fine sands, and they are susceptible to liquefaction, as is represented and reflected from the pore water pressure response under different conditions. Now, if you look at the results here, so we can see that the pore water pressure response at fifth cycle, that is very large, very huge, and we can actually conclude that for these soils, the liquefaction resistance is very low, and cyclic these results show that they better actually simulate the results, and it was also observed during the field that the people have observed, as well as the structural damage that was manifested from the phenomena of liquefaction. Now, the conclusions from the study are actually very large pore water pressures under both monotonic as well as cyclic conditions that may lead to static and cyclic liquefaction. In cyclic liquefaction, it has been manifested during the earthquakes there, like 1956 earthquake and as well as 2001 earthquake. Now, in case of cohesionless soils, granular soils, it is actually the fine content that control the you can say the constitutive behavior of the soils. However, for these clayey soils, or you can say cohesive soils, it was actually the plasticity index rather than the fines content. Now, cyclic simple shear tests, they actually resulted in pore water pressure that was actually 1.3 times that of the cyclic triaxial. So we can say that the cyclic triaxial that actually underestimates the pore water pressure development, which and it in turn actually overestimates the liquefaction resistance. So we have to take care of this the results from different tests also. So the rate and magnitude of this pore water pressure generation, so it was actually decreasing with fines content as well as plasticity index. So we can conclude that cohesionless soils with very low plasticity index, they are most susceptible to liquefaction, and it has been actually observed during these earthquakes also. So these are the references here. Yeah.
All right.
So I'm open to any questions.
Well, thank you very much, Majid. Certainly a lot of effort in getting all of those samples and running all of the tests that you did there. Thinking about, I'll throw a question out if, and certainly my others can join in here. Thinking about your conclusion that cyclic shear versus cyclic triaxial is showing that cyclic shear is higher, gives a higher pore pressure ratio than cyclic triaxial. You know what, and you said it, that cyclic triaxial is tending to underpredict. When you say that, is that a sense that cyclic shear is then perhaps a more conservative test, or that it is capturing a behavior of the soil that is more realistic? What do you, or how do you kind of reconcile the two, and which do you choose as the truth versus which one is better there? So please.
Yeah, thank you, Professor Brenton. Actually, so what happens in cyclic triaxial test, the loading is actually in the axial direction. However, in seismic, in earthquake loading, so the shear waves travel upwards in the horizontal direction. So in that case, it is the cyclic simple shear test where the loading is into the horizontal this direction that actually simulates field condition better. And that is why that we can safely say that it is cyclic simple shear test that represents the field condition better, and we should be actually using that for the seismic analysis.
Very good, thank you. Is there any other questions in the audience? Anyone else want to ask anything of Majid? Well, again, thank you very much for your presentation, Majid, and thank you for watching your time. Please stay around, and we'll see if we have some time for additional discussion and Q&A at the end.
Yeah.
Very good. Thankfully, we are
Now
we
we
are
invite
lucky to.
Padmanabhan.
Yes, exactly. We are lucky to have Padmanabhan back. He is going to discuss from the Indira Gandhi Center for Atomic Research the efficacy of consolidation grouting in improving the dynamic characteristics of nuclear facility foundation strata. If you wouldn't mind sharing your screen, good, and making sure you are unmuted, that would all be very good. Good, we can see you and hear you. Thank you.
Yeah, thank you. Thank you very much. So in this moment, I would like to thank the organizer for giving an opportunity to present our work in this conference. So basically, I will be presenting the work which we have carried out for the part of as a part of our geotechnical investigation and characterization for a nuclear facility site, which is located on South India. So begin with, we know the nuclear power plant structures are basically, they are designed for various type of loads like dead weight, dead load, live load, and then earthquake loads, and complex soil structure interactions analysis were carried out. And we need to construct the nuclear power plant structures, and we need to support the structures on a stable foundation strata, so that during the operation of the nuclear power plant structures, there are no adverse impact on the various structure system and components of the nuclear power plants, because any adverse event will finally lead into the radioactivity release to the general public, which is not warranted. So in that aspect, basically these structures are founded on a competent rock strata where we have sufficient bearing capacity, so that without any uncertainties, we can transfer all the loads which is coming from both dead weight and as well as the live loads and earthquake loads to the foundation media. Generally, if you see, this order of the load is around 250 ton per meter square for a normal nuclear reactor. So to transfer the load, we need to have a competent strata like rock mass. So basically, this rock mass availability depends on the stratigraphy of the site. Which see generally in our South India, we get this type of bearing capacity for a rock strata at around 15 meter to 20 meter below ground level. So, but even though we assume the bearing capacity based on the geotechnical investigations, because of the importance of the structure, we need to, after excavation and after reaching the founding level, we need to carry out the extensive geotechnical investigations and confirmatory investigations to ascertain the bearing capacity, as well as to identify any surprises like fissures, fractures, joints, weak zones, etc. in the founding media, so that which we can be treated, so that there is no safety related issues with respect to the nuclear power plants. And this treatment is also required to increase the deformability characters of the foundation media, and also to reduce the foundation uplift pressure, which are possibly it can occur. So the current practice is to do the excavation of around 15 meter to 20 meter below ground level and reach the hard rock strata, and then do the very detailed geological mapping and identify the weaker zones, and then later take up the ground improvement techniques, ground improvement by using consolidation grouting or other methods. So, but in the current practice, the efficacy of the grouting, basically the consolidation grouting, whatever we carried out to have a compact foundation strata, it measured in terms of the permeability values. That means we carry out the permeability test before grouting and after grouting, and the values were compared. And then if the permeability is reduced, we just strata is improved. But nevertheless, this dynamic properties of the foundation strata is never studied, and we can estimate the parameters. So in this particular, So in this particular facility, we have reached the foundation strata around 15 to 20 meter below ground level, and then we carried out from the geotechnical investigations, we could establish the founding level through before the excavation itself. And then we established the founding level as around 15 to 20 meter. And then rock patterns were arrived. Then subsequently, when the geological mapping was carried out, we could able to identify there are certain weak zones in the foundation strata. So we did an extensive geological mapping for around 1,15,000 square meter, and then the foundation strata were mapped. Basically, the foundation strata is moderately weathered rock. It is made up of charnocate type of rock. So this photograph shows the foundation strata, and we have established the rock mass rating of the foundation strata. And the foundation strata was varying from moderately weathered to slightly weathered and fresh rock. The RMR value, that means the rock mass rating, was varying from around 50 to 60. And there were some few surprises like dike intrusion also in the founding strata, but it was a compact dike. So in that way, there was not much problem with our foundation design. Then subsequent to the mapping, yeah, this is another another slide which shows the importance of the important features which we could able to obtain from the mapping. The foundation strata is primarily comprising of charnocate type rock, and these rocks are classified into fresh to moderately weathered rock. And there are various discontinuities and weak strata were observed, with the thickness varying from few centimeters to several meters. And the rock mass rating also was varying from 48 to 77 meter. And as per the rock mass classifications, this rock means foundation rock is classified as a moderately weathered rock. Then subsequently, after exposing the foundation rock, we have carried out the grouting. And before taking up the grouting, the permeabilities of the foundation strata was established. And if the permeability is more than 1 lugeon, that strata is considered as a groutable strata, and then we executed the grouting with a pattern of grout holes. And the grout holes, generally it is drilled with rotary drills, and grout holes of the diameter of 90 mm, and they were drilled up to around 6 meters below the foundation strata, and then grouting was carried out. Then after the grouting, we again established the permeability value by carrying out the permeability test. And in this project, around 250 holes were drilled at a spacing of around 10 meters. That is basically primary holes. Then subsequently, the primary holes, we did permeability test, and then we did the secondary holes. Then again, the permeability value were considered. Then after the improvement, we could able to observe the permeability values around less than 1 lugeon. So this graph shows a typical grout hole lugeon value, wherein the lugeon values were high, that is more than around 2.37 to 4.39 for a different pressure. And we could able to obtain a lugeon value of around 1 after the grouting, so which shows the void is getting filled. So this is the general practice, but considering the various advanced field methods, investigation methods like multi-channel analysis of surface waves and seismic cross-hole tests availability, we can effectively utilize this test to find out the improvement in the engineering properties of the foundation strata after the consolidation grouting. So in that way, this multi-channel analysis of surface wave tests were conducted in this particular site before taking up the consolidation grouting and after taking up the consolidation grouting. Around 6 profiles were considered for carrying out this test. So this figure clearly shows, prior to the consolidation grouting, there are the weak zones where the shear wave velocity of the foundation strata is around 1,800 meters per second. And after subsequently the consolidation grouting, we could see the improvement in the foundation strata. So the shear wave velocity was increased to around 2,100 meters per second. So to conclude, the study indicated that the top layer consists of weak zone, which is having a comparatively lesser velocity, shear wave velocity of around 1,800 meters per second, and that was extending around 15 meters below the ground level. So after consolidation grouting, and with respect to the conventional permeability test, we could able to establish the efficacy of the grouting, but additionally the MAS tests were conducted to assess the improvement in the shear wave velocity. So we observed around 16% of the shear wave velocity is getting increased by the consolidation and grouting. So which in turn improves the shear modulus of the structure foundation strata, which is an important parameter to important parameter and input for carrying out the foundation system. So we observed around 36% of the shear modulus is getting increased by the consolidation grouting. So these values were effectively used. It can be effectively used for the design of foundations. Thank you.
Thank you very much. And again, thank you for watching your time. Let me start my video. I don't see any questions coming in on the Q&A quite yet, but did you get a sense through MASW or cross-hole seismic tests what the vertical extent of the improvement was? Based, it looks, and I guess how deep did the did that improvement go relative to the two color plots that you just showed, showing the improvement from pre and post grouting?
Yeah, there is definitely an improvement. Even though we have done the seismic cross holes and MASW tests we did earlier, so there was an improvement.
Mm-hmm. So you could see that the vertical extent of the improvement extended down well into the 15-meter zone that you were talking about.
Yes, around 15 meter we could able to see that. Yes.
Yeah, very
because
nice.
This top layer, after exposing the ground surface, we were not able to ascertain what is the depth of the weak zone. So then after grouting, yes, we could able to see that, and the MASW really gives that depth of the weak zones.
Yes, certainly. Any other challenges in collecting that data before and after?
Yeah, the basic challenges were actually the discrete number of the boreholes. So before the before the investigations with the discrete number of data, what we did is actually here in this project, we have deployed the seismic refraction survey in the beginning stage itself with a closer spacing. So that able to provide very detailed data regarding the bedrock topography. Before excavation itself, we could able to identify more or less on a closer interval. So that was one of the challenge. And then,
yes, I can imagine. And how did the refraction or the reflection survey match up with what you noticed or what you observed when you excavated?
Most of the refraction details were matching for the topography, rock topography, whatever we could able to identify. But these weak zones we were not able to delineate with the seismic refraction. For that we have done the overall excavation and then we did the confirmatory investigations.
Yes, that makes sense. Well, thank you very much for that interesting presentation.
Thank you.
We have a few more minutes, I believe. I don't know, Dr. Rao, if you saw that our second speaker, Prudvi Mamidala, had made it back on, just to make sure that we aren't forgetting anyone. Okay, well, that's a shame. One other question that came up during the last presentation was for Majid Hussain, and he was asked how much time was the saturation of the clay specimens, and any suggestion to saturate that clay specimen. Majid, would you like to come back on and answer that live?
Yeah, that I have answered in text, but I'm happy to answer it live. So actually what happens is that it depends on the type and the amount of the clay. So if it is a moderate melt mineral, and for a given amount of clay, it will take time. So we have achieved for this type of soils this saturation up to around 3 to 6 days. So higher the clay content, higher was the time taken for the saturation. And we actually did moist stamping, then CO2 saturation, water flushing, after that CO2 saturation, and then applied back pressure. So we were actually able to saturate the specimens within 1 week, clay specimens, and sand specimens that took only actually 6 to 8 hours on.
Very good, thank you. And I guess if there are any other questions, please go ahead and type them into the chat box. Dr. Rao, did you have any follow-ups that you wanted to ask?
Majid, currently, what is your affiliation?
So I am at I.I.T Srinagar.
You are a faculty there now?
Yes, yeah.
Okay, thank you.
Well, again, I guess one other thing that we can, if we can bring back Dr. Vinod and perhaps, where is it, Mohit Mistry? There was something that I think kind of came out of their presentations looking at the reinforcement aspects of waste tires and coir fiber reinforcement.
Thank you. I was just trying to remember the question that I have tried asked to Mohit. I'm not sure about this round. My question is mostly around the resilient modulus. If he is trying to apply this for transport infrastructure, I think in addition to the CBR, I think it's critical that we should be looking at the resilient modulus of this mixture, which is critical. I think because we are adding a low stiffness material like rubber into a high stiffness material, so it can seriously affect the performance of the infrastructure. So it's very important that we look at that property in depth before applying this material for infrastructure construction. So that's basically a comment for Mohit to look at this material in bit more depth before applying for.
Yeah, you are right, but unfortunately, Mohit is not there at the moment.
That's all right.
Yeah.
And a quick comment to Padmanabhan. I think it's a interesting work, and it's a challenge associated when it comes to the application of MASW in the field. And monitoring those data critically and analyze actually the improvement factor. I think that is really challenging in the field scenario. So it's a great work. Thank you, Padmanabhan.
Yeah, thank you, Dr. Vinod. Yeah.
Any other questions?
Well, going back very quickly, since we have a few more minutes, going back to Dr. Vinod's discussions and some of the discussion that happened when we had to cut that short. Thinking back on the biodegradability of coir geotextiles and its application to slopes versus applications to a more buried environment, has there been a lot of work done in looking at how the effect of the coir being buried and perhaps in a low oxygen, kind of low and perhaps low moisture environment changes the long-term life of the coir?
Yes, we did find some work in that aspect, like degradation of coir fibers under different soil condition. For example, pH of the soil, it can be influenced for the degradation purpose. What we observed is if this material is used for a kind of an acid sulfate soil, prone soil, degradation is pretty fast. So it's very quick, and you won't get any kind of behavior or any kind of strength or response that you are referring to these kind of materials. But there are soils that we believe that can be used comfortably within that span of time. For example, if you are looking at short term the constructions which we required only for few years, or for example for the major construction we construct the small scale construction, we can easily adopt these kind of materials for those kind of infrastructure development. So in addition, what the motivation is to promote natural materials for more kind of an infrastructure construction and reduce probably the application of plastics into the soil. I think that is an agenda that probably looking at indirectly through this work.
Yeah, certainly.
Because we have found out, because a lot of plastic waste happening these days, and we are looking at different methodology in looking at using these plastic waste for infrastructure development, and we don't want to create more plastic waste. And in future, probably we will be looking more into these kind of natural materials. But only thing is that we need to identify the correct application. And only way that we can look at correct application is to look at this material in depth and understand this behavior in different soil conditions, degradation, etc. And then probably we should be able to apply this to the correct infrastructure construction.
And I think that is a good comment for both for any soil additive, whether it be waste tire fibers or coir or or plastics. So that is a good place to kind of wrap up what we have discussed. Thank you to all of our presenters. I know that we sometimes ask our student presenters to cover many years of their lives in only 8 minutes, and that is often very much a challenge. We ask our least experienced people to do something that is very, very difficult. And so I appreciate the efforts in all cases. Thank you, Dr. Rao, for co-chairing and stepping in as the co-chair. And I hope that everyone else enjoys the rest of this 7th International Conference. Dr. Rao, do you have any comments or concerns?
Regarding what Vinod was saying, that we need to look into new application methods for these coir fibers instead of conventionally just switching over from synthetic to coir. As he said, we have to look for new methods. For example, my colleagues at Structural Engineering of I.I.Sc, they were working on adding these coir fibers to rammed earth.
Excellent.
So it substantially improves. And one advantage with the rammed earth application is, unlike the ground applications where you don't have adequate water for that to decay.
Correct.
So mostly it will be in the dry form, and it can remain in the same strength for a longer time when compared to subsoil applications.
Yep.
So they are doing very good, and also they are use some kind of treatment for the
coir fibers
before actually using it in the rammed earth.
Yep.
So there are like that many applications are there, but we have to explore. Yes, it's a very good starting, and hope Vinod will do much more research on this.
Thank you very much.
Yeah. So we had a nice session with Vinod's lecture, starting with on soft soils with the coir and synthetic comparisons, and then how it can improve the properties and other things. And then followed by lecture by Aarti on sand compaction columns.
Very quickly, there is another question that comes in for Aarti since we've been talking. I don't believe she is still on the.
No, she's not there. She has gone to take the class. She came in between the classes.
But I would suggest that Shravan Kumar does find her email address and ask the question on efficiency of sand columns and mitigating liquefaction, particularly in already cohesionless soils.
Actually, there is a way they can look at later also and answer. That facility is there in this system.
Very good. Well, I hope that is something that she is able to do.
Yeah, and the lecture by Mohit is very interesting, using waste tire fibers reinforcement. And then followed by Majid's lecture on static and cyclic response. Then Padmanabhan's on consolidation grouting to improve dynamic characteristics. So we had a diversified lectures in the whole session. And of course, all of them are very interesting, and most of them have practical applications. Very good. We had a nice time. So I thank all the speakers, and then the chair on behalf of organizing committee. So thank you very much for chairing the session and completing the session much before the scheduled time. We are ahead of almost 5 minutes. Thank you very much. Thank you.
Yes. Thank you to everyone.
Thank you.
Thank you all.
Hello, Brent.
Hello, Dr. Sarathi. Nice to see you.
Nice to see you, sir. Nice to see you. Thank you for being a part of this program and chairing this session. And I heard Vinod through the platform. It was a very nice presentation. So I had to go to another hall to relieve my other colleague. Just now I came back to say hello to you. So anyway, thank you, sir, for being part of this.
So thank you all. We'll close and we'll go for the next plenary session starting at 4:30.